Okay, so let's switch over to writing mode. There we go. So last class, we talked about net change. We talked about what happens when you integrate a function, or when you have a function defined by an integral. That's the better way to say it. So if you have like this function defined by an integral, we find out that the function inside of the integral is the rate of change, and how that works. And that sort of makes sense because if you look at like a picture like this, you can see that here's your function that you're integrating. Because the function's decreasing, you're adding less area as time goes on. So we discussed that last class. Now we're moving on to a new topic. And our new topic is U substitution. Okay, so before I jump into this, I need to give you like a little background about like what the hell is this about. So let's think about this. I'm having a hard time like clicking and typing on stuff. I like don't have a big enough keyboard to do everything. Or sorry, desk. I have my book, I have my keyboard, and I have my little writing thing, and like they're all competing for space, and it's a little annoying. So let's go back and think about integration. Integration is all about finding the area under f of x between x equals a and x equals b and above the y-axis. Right? That's what we use the definite integral for. That's what it's defined to be. So we write that as integral a to b f of x dx. Now, how did we actually figure this out? Honest question. Like when we first started. How did we actually figure it out? How? How did we figure it out? Okay, the antiderivative was later. The approximation was afterwards. So what we did was, let's go with the approximation answer. What we did was we had an approximation for the area, which is a Riemann sum, right? We summed up some m number of rectangles. We took their heights determined by like the left or right endpoint. We multiplied by their widths. And then to actually give us the real area, we took the limit of that. Now this is a real pain. Nobody wants to do this, right? Okay, so then we figured out that if you have the antiderivative, which is big F, and you know that big F is the antiderivative of little f, if you take the derivative of big F and you get little f back, right, that's the antiderivative. We found out that instead of having to do this horrible limit sigma calculation, you could just do f of b minus f of a. Okay, so that's like where we are right now. Like, okay, we have this fundamental theorem of calculus. We know that the antiderivative is a much easier and simpler way to calculate this definite integral. And now we're concerned about being able to find antiderivatives. We need methods to find antiderivatives. Because we need antiderivatives to solve these integrals now. Does that sort of make sense? Like, we gave up doing this limit calculation because it was easier if you knew the antiderivative. So now we need to talk about, like, well, how are you actually going to find these dang antiderivatives? Well, in some cases it's pretty straightforward because there's a duality, it's called, between the antiderivative and the function. Let's talk about this duality. We know that the derivative of the antiderivative equals your function. And the dual statement of this, I guess you could sort of proper but not quite, is that the indefinite integral of f of x dx is big F of x plus c. Did someone have a question? I thought I heard something. Yeah, I keep on hearing that too. I also have a loud beeping. I'm going to investigate my beeping, so just give me 1 second. Because the loud beeping and the weird voice in the background is really creeping me out, so uno momento. Oh, the beeping must be from the washing machine. Just pause. Oh, that sucks. Hey, when this timer goes off, I need you to take out this tea, okay? Did you hear me? No. When the timer goes off, you take out the tea, you press cancel on the timer.
Do I turn the heat off too?
What?
Do I turn the heat off too?
It's already off. Okay, I figured out what one of the beeping was. So, I have like sink issues right now, and I had to like stop my washing machine because like when it drains, it's like going into the water disposal, and then the water leaks out of it. So it keeps on beeping in the background because it's on pause, reminding me to keep it going. But I can't start it because the repairman hasn't come here yet. Yeah, it does suck. Okay, so anyways, we're just gonna have to deal with it. It will suck. Okay, so why am I writing this? Because this gives you a method. Yeah, hopefully it gets you. Hopefully. This gives you a method to figure out antiderivatives. Okay, for instance, we know that x squared over 2 is the antiderivative of of x, because the derivative of x squared over 2 is x, which means you can rewrite it as antiderivative of x dx equals x squared plus 2 plus c. So this right here gives you a formula to take a derivative statement and rewrite it into an integral statement. If the derivative of this thing equals that thing, then the antiderivative of this one equals that one. So let's look over here. The derivative of x squared over 2 is x, which means that the antiderivative of x is x squared over 2. Okay, so you can rewrite derivative statements as antiderivative statements. So you can rewrite derivative statements as antiderivative statements. So in other words, any derivative rule that you know can be turned into an integral rule to find an antiderivative. So that's good so far. Like all that stuff we learned last semester, or that you learned last semester about derivatives, still applies. And in the sense that you can rewrite it into an integral or an antiderivative. Okay. Like, quick example, like one more. We know that, what's the derivative of sine? Cool. So if the derivative of sine is cosine, that means that the antiderivative of cosine is sine. You now have an antiderivative. So that's what I mean by you can take, the derivative of cosine is minus sine. You have those two switched. First, let me put that in the chat. But, so my point in showing you this is that we took a derivative statement and we rewrote it as an antiderivative statement. You can always do this. Okay, that's how we're usually going to find our antiderivatives. However, sometimes this is not very easy to do. Like for this, obviously, like this is not that bad. Like you look at it and you're like, oh, if I'm starting off like, oh, I need to know the derivative of cosine. If I want the antiderivative of cosine, you're like, oh, well, the derivative of sine is cosine, so there we go. I found the antiderivative. Like sometimes it's not that easy. So let's give you like an example. Example of a more difficult. It says there's an error. What does it say? Okay, weird. But I know that someone's audio is not encrypted for some weird reason. I think they're probably going in through a phone. Is anyone here going into the audio through a phone? Let's look. It says there's like some weird exception about some encryption. Yeah, I see it. I see how you're like me. I was like, what the hell is this? It's like this little error, like it's not completely encrypted. Yeah, you have done it every day, but I didn't like notice the little, I noticed that you had done it, but I didn't notice the little, it's like this warning that keeps popping up on my screen saying that like, you should be careful, not everything is encrypted. And I was like, what the hell's this one exception? And then it had your name and it's like, oh yeah, he's the one on the phone, so that makes sense. Now the NSA knows what we're doing. Okay, so let's do an example of a more difficult problem. So let's say that you're looking at the antiderivative of, I don't know, x squared minus 3 times 2x dx. You're like, okay, what's the antiderivative of this? Because let's say you need to solve some definite integral. Looking at this, it may not be obvious right away as to what your antiderivative would be, because like there's no rule that immediately pops into your mind. You're like, I want something. I'm looking for some function whose derivative is equal to x squared minus 3 times 2x. So you're looking at that and you're like, okay. You could like multiply it through and you'd get 2x cubed minus 6x, and now you could figure it out, but like that's like a little bit of work. Okay, so there's an interesting technique we're going to use to make problems like this simpler, and it's called substitution. So we're going to come up with a technique called substitution. And basically what this technique is that you're going to rewrite your function so it's easier to recognize what derivative rule you need to use. Like you're trying to figure out what function has this as its derivative. You're going to rewrite all this and like it'll be easier to see what that is basically. So what you do is you look at the stuff that you're taking the antiderivative of. We'll call that f of x. Or let's just look at that stuff. We'll look at this x squared. Let's not call it anything yet. Let's just look at what we're taking the antiderivative of. We have our x squared minus 3 2x. So if you look at x squared minus 3 and 2x, what could you do to x squared minus 3 that would make it very similar to 2x? This is what I mean by rewriting it. So there's something going on here. I like drew the arrow in a particular way. What's the relationship between x squared minus 3 and 2x? Yeah. So you're like, oh, that's weird. Like 2x literally is the derivative of x squared minus 3. So what I'm going to do is I'm going to call x squared minus 3u. So that's my substitution. Okay, so now this statement can be rewritten. The x squared minus 3 is u. And you notice that if you take the derivative of u, you get 2x. So now you get u times du dx. Yeah, this is the integral version of the chain rule, oddly enough. So the chain rule is all about rewriting your function when you want to take a derivative. And remember how I said that all derivative rules can be rewritten as integral rules? We're sort of working towards there. Because this should be sort of similar to the chain rule. So you look at this, the x squared minus 3 times 2x, you can rewrite that as u times du dx. Which means my original integral can be rewritten as integral. The x squared minus 3 is u. The 2x is du dx. And then you have your dx. And what's sort of cool about this is that you see how these dx's, you can sort of think of them as canceling. And now you get a new integral, u du. So I started off up here. I replaced the x squared minus 3 with u, like what I said up here. I replaced the 2x with du dx, and then the dx is just from the dx right here. The dx differentials canceled, leaving me with just u du. No, these are still indefinite because there are no bounds. There's no a or b. Now, if you were to integrate u du, what do you get? So this is u to the first du. What's the antiderivative of that? U squared over 2 plus what? We can't forget it. C, thank you. Which means, so we put this back in. What is u squared over 2? Well, u was x squared minus 3. We're going to square that. We're going to divide that by 2. And then add c to it. That is the antiderivative that we're looking for. Boom. That is the solution to my integral x squared minus 3 2x dx. Bam! And you can verify this. If you took the derivative of x squared minus 3 squared over 2 plus c, you would get you would get this stuff as the derivative of big F here. So practically speaking, this is how you do this. We're going to get a little theoretical in here in a moment here and talk about like why this always works. Okay. So can I scroll down now? Does anyone need to look at this more? Okay. Cool. So, like, let's talk about why does this work? Okay, the reason it works goes back to this duality between the derivative of the antiderivative equals your original function, and that can be rewritten as the antiderivative of f of x equals big F of x. Okay, so what we're going to do is we're going to think of the chain rule. Do we remember the chain rule? You're taking the derivative of a composition. What is the chain rule? If you take the derivative of f of g of x, what do you get? Let's see if people remember. F prime g of x close. It's f prime of g of x. There's more though. We're missing something. Times g prime, yeah. Okay, why is it not letting me do this? There we go. Now, because every derivative rule can be rewritten as an integral rule, that now means that the antiderivative of f prime g of x times g prime dx has as its antiderivative f of g of x plus c. Now you look at this and you're like, well, that is ugly. Like, why would I want this rule? Well, we can actually simplify it a little here. Do you remember how there were two different versions of the chain rule? One of them used variables instead of like f of g of x and stuff like that. Do you remember what we called g of x in that version of the chain rule? Like, what did we set it equal to? U. Good. So we're going to do some rewriting here. So this f of g of x plus c, that is now equal to f of u plus c. Right? Because the g of x got replaced with u. This is now f prime of u. Okay. G prime is du dx. So we can replace g prime with du dx, and then we have our dx. So what do you notice with those dx's? What happens to them? Yeah. Boom, boom. And now you get some new version. You get f of u plus c equals f prime u du. So in other words, if you're taking the integral of f prime, the integral and the prime cancel and you get f. Okay, so this is like the two ways you can think about u substitution. You're starting off with some really complicated thing like up here. This looks complicated. You're like, I never want to look at this. And you're like, hey, I know what I'll do. I'll make a substitution. Anything called u, or sorry, anything called, I'm going to take all of this stuff, which is g of x, whatever the hell that happens to be, and I'm going to replace it with u. And then it simplifies what you're going to get. This more complicated thing gets boiled down to this, which then it looks simple to integrate. That's the whole idea behind this. You take something complicated, substitute stuff away, it becomes simple, and they're like, oh, I know how to integrate that. That's not that bad. Very similar to the chain rule. You start off with something very complicated with like a bunch of compositions. You do some rewriting, boom, you can take the integral fairly quickly. Okay. So to do the substitution, you're going to need to notice like what you should substitute and where. And you're going to need to make sure that everything lines up properly. So let's go through an example. Wait, actually, have people looked at this enough so that you can refer to it later? Because you're going to need to look at this. Can I move away from here? Just want to make sure when I move away, people have like been able to see it enough. Okay, cool. So let's scroll away from this. Let's go for a scroll. So example, let's integrate this thing. We're doing the indefinite integral of 6x 3x squared plus 4 to the 4th dx. So when you're doing this, you need to distinguish what you're going to substitute. And usually the way you do that, so you find the substitution by looking for two parts that are derivatives of each other. And you can see right away that the two parts are not that difficult to find. If you look at 3x squared plus 4 and 6x, what do you notice about them right away? Well, if you call u 3x squared plus 4, then what you get is that du dx equals 6x. And you're like, oh snap. I can like start rewriting some stuff here. So you've made your substitution, and you can now tell that your integral is going to be, well, the 3x squared plus 4, that's u, and what was happening to 3x squared plus 4, it was being raised to the 4th. So this is all of that stuff. And then you can multiply that by 6x, but 6x is replaced by du dx. So du dx is that 6x. And then you have your dx. Right? This goes with that. Okay, when you do this, you have to be very careful. You need to make sure that everything is replaced. You can't just like leave some stuff dangling. Okay, so you need to check to make sure that everything has been replaced. Yeah, and we're going to get to that later, but yeah, that's a good point. Like, if you didn't have 6x, it all needs to match. There will be ways around that later, but for now, it'd be like, well, it's not working, it's not matching. Okay, and then you look at this and you're like, okay, I can erase those dx's. Hooray. Or they cancel, whatever. So what are we doing? We're integrating u to the 4th du, which is simple to integrate. You get u to the 5th over 5 plus c. So to rewrite that in terms of x, you just plug the x back in. So I'm going to get 3x squared to the 4th, all raised to the 5th, divided by 5 plus c. That is the antiderivative of my original question. So any questions on any of the steps on what we did? Are we sort of seeing how to choose the substitution, what you're looking for? Anything we want to ask so far? Okay, cool. Looks like people are good. Okay, I just want to take a moment break because I need to go to the bathroom. So just give me like 1 minute. Okay, I'm back. Okay, so let's do another example. Scroll down, go for a scroll. Example. Let's integrate, find the antiderivative of z square root of z squared minus 5 dz. So remember, how do you start this? You start looking for a substitution by finding something that might be equal to the derivative of something else. So you're like, z squared minus 5 and z. Those are pretty close to being derivatives. If you set u equal to z squared minus 5, then your du dx would end up being 2z. But then you look at this and you're like, shit, like, actually, this should be du dz, my bad. Not du dx. You look at this, you're like, I have z here, but this is 2z. You can actually just rearrange some of this stuff. So let's divide both sides by 2, and you'll get 1/2 of du dz equals z. And you're like, oh yay, this now matches with that. And actually, you could rearrange this a little more. Do you see this dz right here? There's a matching one right here. So I can multiply both sides of that equation by dz, and I get 1/2 du equals z times dz. The z and the dz now match completely with that. So what can I replace those two things with? 1/2 du. So the z and the dz can be replaced with 1/2 du, and the square root of z squared minus 5, that's the square root of u. So let me pause. Everything is accounted for. This 1/2 du came from z dz over here, and this square root of u came from that part. Notice everything has been completely changed. And now it's easy to integrate. I am integrating u to the 1/2 du, which will be u to the 3/2 times 2/3 plus c, and then I replace what u was. So I'm going to get 2/3 z squared minus 5 to the 3/2 plus c. That's my antiderivative. So it works even if everything doesn't match up, but you might have to be creative about moving terms around. Right? Remember, the derivative of u was 2z, but I only had a z. You can divide that 2 to the other side, and that's why you end up with that 1/2 there. You don't have to multiply it by 1/2 because I did that step over here. The 2 became the 1/2 when I moved it to the other side of the equation, which is why it ended up right there. Does that make sense? Because 1/2 du is equal to z dz. I had a z and a dz, so it can be replaced with a 1/2 du. Does that answer your question, Sid? Oh, crap. I forgot about the 1/2. Thank you for pointing that out. I forgot about the 1/2. Right? The 1/2 was like sitting in there and I just completely forgot about it. So yeah, you get... Well, actually, you don't. You get 1/2, and then what's the 1/2 times 2/3? That 1/2 will cancel with the 2. So you actually get 1/3. Because you get... Oops, okay, let me move this stuff. Okay, so you get, oops, sorry. So you get 1/2 integral u to the 1/2 du, which will be 1/2 times 2/3 u to the 3/2 plus c. The 2's here cancel, so it becomes 1/3. That's your antiderivative. Okay. Let's see, it's 11:54. What time did we go until? Did we go until like 12:10? Okay, cool. We got time. We'll do another one. Yeah, let's do another one. So sometimes you have to be creative about the substitutions and what you do. So example, let's say that you've decided you want the antiderivative of x divided by the square root of x minus 1 dx. Okay, this looks complicated, so you're like, okay, well, let's reverse chain rule this thing, or you substitute this thing to find the antiderivative. And what's the problem? Normally you're looking for two things that have what sort of relationship? Like the two pieces you're looking for to make your u substitution. Yeah, one needs to be the derivative of the other. Do you see that anywhere here? No, you're like, you have x and you have x minus 1. You're like, oh no, this is not good. So, let's see, like you could possibly say, well, let's just see what happens if you do like u equals x minus 1. Then your du dx would just be 1. Which means that du just equals dx. Now if you tried to make the change, you'd get integral, and you'd get a square root of u on the bottom. That dx could be replaced with du, but then what are you left over with that's like still unreplaced? Yeah, you've got this x, so you're like, okay, that's not going to work out because you're only done with the u substitution if like everything at the end is just u's. So you're like, this is not going to work. So we're going to erase that. So that one doesn't work. So you have to try something else. Okay. And actually, you can. You just have to be a little creative about it. I need to replace x. Which means that I can actually take this equation right here and solve it for x. And that's what I could replace it with. So in other words, u plus 1 equals x. And now I can go back up and I can be like, okay, that's equal to the integral. On the bottom, you get square root u. The dx gets replaced with du. And then now what do I get on the top here? U plus 1. And you're like, oh shit, I did it. I did it. So it actually does work. You just have to be careful about what you're doing. And you can finish solving the problem. You can turn this into two integrals. You get u over u to the half over 1 over u. Actually, let's just leave it as 1. But we'll just change everything to exponents. So you're going to get the integral of u to the 1/2 plus u to the negative 1/2. And the antiderivative of that is not too difficult. That's going to be u to the 3/2 times 2/3 plus u to the 1/2 times 2 plus c. And then now you can replace the x's back. So remember that u equals x minus 1, so you get 2/3 x minus 1 to the 3/2 plus 2 x minus 1 to the 1/2 plus c. And there's your f of x. Boom. And we can scroll up a little so you can see the previous work. There you go. So questions on what I did there. Just making sense? Okay. Cool. Any questions on the steps? Do we see the replacements that I'm making? Does it make sense how I'm choosing the replacements? How I'm going from the white to the blue and then to the green? Any questions about any of those steps there? Okay, cool. Okay, so we've done u substitution with indefinite integrals so far. So what do you think we're going to combine u substitution with now? These have all been indefinite integrals. They have no bounds. So what do you think we're going to do now? Yeah, we're going to do it with definite integrals. So let's do an example where it's like now we're calculating an area. So definite integral example. So let's say that you're integrating from 0 to 1 x squared 1 plus 2x cubed all to the 5th dx. So this thing here, that's your f of x, and this is your x equals a, and this is your x equals b. Right? So like practically speaking, you have this function x y axis, you got your function f of x, and you want to find the area between x equals 0 and x equals 1. I know that like that should be over there, but I didn't want it there because it looks really ugly when you do that. Okay, so you want this area, right? Now this is like a complicated, ugly function. Like if you wanted to find the antiderivative of this, like you could multiply all that out, like expand that stuff to the 5th power, but it's easier to do a substitution. Because you notice that the stuff inside here, what's the derivative of 2x cubed? Well, it's going to be pretty close to x squared, right? Like those definitely are pretty close to being derivatives of each other. So you're like, okay, let's set my u up to be 1 plus 2x cubed, which means that my du dx will be 6x squared. But I just want the x squared, and I'd also like to replace the dx at the same time. So I can divide by 6 on both sides and multiply by dx. So I'm going to get 1/6 du equals x squared dx. Right? That x squared dx is going to replace all that stuff in green up there, and I can replace it with the 1/6 du. Yeah, just person who says they're going to leave, you're going to need to say I was here. Okay, so now you can make this change. You can say, okay, I'm integrating. We'll forget about what I'm integrating for a moment. But the 1 plus 2x cubed, that's u. And it's now u to the 5th. And what used to be x squared dx, I can now replace with 1/6 du. So you're like, yay, success. This is going to be way easier to integrate. But the problem is I need to know those bounds. So the old bounds of 0 and 1, what variable was that taking into account? If I was integrating from 0 to 1, what variable was that working with? Like if you look just right above x. But what's my variable I'm going to use now for this integration? U. So you need to make an appropriate change. So you need to change the number. You need to change the bounds to be in terms of u, and that's actually quite easy to do because I can use this to figure out how to change them. So what do you get if you plug in 0 into u, and what do you get if you plug 1 into u? Well, you're going to get 1 plus 2 times 0 cubed, which is just 1. And you'll get 1 plus 2 times 1 cubed, which is 3. So my new bounds are 1 to 3. So do you see how I had to plug the old numbers, which were x values, into the formula to translate them to u values? Okay, now you can go forward. You're like, okay, factor out that's 1/6. I'm integrating from 1 to 3. This is u to the 5th du, which means my antiderivative is u to the 6th over 6th. So I'm going to plug my values into that. I'm going to get 3 to the 6th divided by 6th. Oh, let's not forget about the 1/6 out in front. So I've got my 1/6 out in front. Plug my 3 into my antiderivative, which is 3 to the 6th over 6th, minus, now plug my 1 in, 1 to the 6th over 6th. Holy crap, that is a horrible number. Three to the 6th minus 1 to the 6th is going to be... holy shit. Okay, I'm going to open a calculator. Alright, you're asking, would it still work if you subbed back? Yeah, you could still sub back to x, but usually that's more work. Like, I've already changed everything to u's, so I'll just keep working with u's. So because I have my u to the... So there's two ways you could do this. You could do it this way, and I'll quickly do the other way. I'll just tell you that after you sometimes it's easier, sometimes it's not. If you simplify all this, you're going to get... Let me just like type it into the calculator really quickly here. You get 182 over 9. Now, the other way you could do this is if you take everything back to x's. So if you're thinking about this in terms of x's, your antiderivative is, what was u equal to in the first place? 1 plus 2x to the third. So you'd have 1 plus 2x to the third to the sixth over sixth. So you would have to plug what was it, 0 and 1 into that. So you would get f of 1 minus f of 0, which would be, you'd end up getting the same thing, but notice it's not going to be that much nicer. 1 plus 2 times 1 to the third to the sixth over 6 minus 1 plus 2 times 0 to the third over 6 over 6. You see how it's like you still are going to have to raise something to the sixth. So it's like, it's not much better converting it back to x's. You might as well just leave it as u's. You're going to have to do the same calculation eventually. What was the reason why we are using the interval as 1, 3? Because 0 and 1 up here was when your variable was x. Now, what's our variable? U, so you need to translate my 0 and 1, which are x values, into u values, which are 1 and 3. And we're basically done here. So I'm going to stop the recording. And before you go, just say I was here. Yes, congratulations. Another day made it through.